So hi to your parents. Okay. Here we go. Chapter 4, y'all. Aaron, what's the title of 4.1?
Extreme values of functions.
Exactly, right? Here we go. Your cards are upside down and right side up. Okay. All right. Huh? Okay. Sure. I don't need it. All right.
It looks like you.
Does that look like Kingsley on the whiteboard?
Yeah, I know. The shape, I think. The hair's kind of it.
All right. Absolute extreme value theorem, aka some people will call it global extreme values. Okay, here we go. Let f be a function with domain, let's call it D, then f of c is da da da. Okay. Let's remind ourselves really quickly. Okay, if I give you this, let's go down forever. Let's call this C. What do we call this point on the top? It is. Okay. So let's revert back to high and low. Do you guys remember that was called absolute maximum? Okay, so that's definitely an absolute maximum. What if I draw it upside down? So what's this guy in the bottom? Absolute minimum, right? So like I said, I told you that this is going to be a bit of review. So here's the formal definition, okay? So let f be a function with the domain D, whatever D is, whatever domain you have. Then f of c is absolute maximum value on this domain, which we call it D, if and only if it fits this definition. F of x, that means just any other value of x, has to be less than or equal to f of c for all x value that is in this domain called D. So let's check that really quickly to see it fits the domain, or the definition I should say. Here's f of c. Would that be a true statement right there? F of c is the absolute max. That means every other x has to be less than or what? Equal to. So is every other x less than or equal to? Yes, it fits the definition. So f of c is definitely an absolute max. Then we will also review absolute minimum. Absolute minimum value, that means talking about the y value, on the same interval which we have called it D, if and only if f of x is now greater than or equal to f of c for all x value within the domain that's called D. So similarly, look at all the x values. That's not c. Is it greater than or equal to f of c? Yeah, so that's why at c, when x is c, f of c is the minimum. So f of c is the minimum value, okay? So let's distinguish between the is and at, okay? If you see the word is, it's talking about the y value of the min and max, okay? So absolute min is 5. That means the y value is 5. Absolute min is at. Okay, so again, if you see the word at, that means talking about the x location. Okay, so I want to make sure those two words are really clear. All right, let's practice really quickly. Can you help me read, Marley, the definition or the instruction for example 1?
Identify each x value at which any absolute extreme value occurs.
Thank you. So it's looking for x location when you have any absolute extreme value, okay? So we're going to look for both absolute min and absolute max. And just put like a min, a max. It's a lot quicker than spelling it all out. Do we have an absolute min? This one goes to Natalis. Yeah? Where is it at? Because it says identify the x value. So absolute min is at what? B. You're right. X equals to B. Would that be okay? Yes. Since this is not labeled, let's call it C for the sake of answering this question. Okay. Do we have an absolute max? Josh Summers. C. So absolute max is at x equals to C. Okay. Easy peasy. Why don't you guys try out B for me and let me know. Do B. Absolute min, absolute max. Once you have an answer, can you compare that with your peeps close the door? Patrick, final answer, absolute min, please.
The absolute min occurs at x equals 5.
Okay, occurs, I'm going to spell exactly what you said. Is Patrick correct? Yes. This one goes to Kingsley, absolute max. At x equals 1. Is that okay? Someone asked me this question in first period. I want to bring it up. What if I change this? Don't change it in your notes. Let's verbally talk about it. What if that's open? Would you have an absolute max? Uh-huh.
Yes, because it says for x is less than or equal to x.
Okay. What is your... Okay, so let's talk about absolute min. Okay, I'm so glad. Would you agree the definition did say for all x values, right? Would you agree? That has to be less than or equal to? Do you have an f of c? In this case, that's really f of 1. Would you agree? Did you even have an f of c? No, right? So if you don't have it, then that means that you can't quantify it. So some of you may argue, let's just pretend this is 14, okay? Some of you may argue, well, my f of 1 could be 13.99. Well, couldn't my f of 1 be higher than that? Like 13.9999, right? Because it's not inclusive, it doesn't exist. Okay? If you can't quantify it, it doesn't exist, then there is no absolute max.
Since it's not an absolute max, wouldn't it be a relative max?
Not at that location. And that location there is nothing. Okay. A relative, or right after this, we're going to define that. A relative or local, or this right here, then would be called a relative or a local max. Right here. So in a little bit, we'll go over the relative or the local. Okay. So if it doesn't exist, if you can't quantify f of c, then you don't have an absolute min or absolute max. Okay. All right. Extreme value theorem. Here we go. If f is continuous on a closed interval, And this brings me back to that open circle that we just made up, okay? If f is a continuous on a closed interval, let's call it from A to B, then f has both maximum and minimum value on the interval. Okay. So in plain English, if you have a closed interval, okay, you are guaranteed to have both. Would you guys agree? Mm-hmm. So that's a closed one. But if you have a non-enclosed interval, are you guaranteed to have both? No, okay? And I can even make one of the sides closed, okay? It doesn't have to be both. So that's the definition. So extreme value theorem says if you have a closed interval, you will guarantee to have both, okay? But if you have an open one, you are not necessarily mean you're going to have both, okay? I mean, you may or you may not. Uh-huh.
It was like a horizontal line close to the end.
Yeah, this also came up during another class. What if you have this? Let's say, yeah, they just all happen to be exactly the same by definition. Yep. What if you have this? It's still the same thing by definition, right? So horizontal line is quite boring. There isn't any, they're not unique. Okay. Huh? I know. Tests are always boring. As teachers, we don't want to give tests. I know. But then we don't. But then we can't assess you. That's another part. Okay. Listen, as teachers, grading is like the last thing that we want to do. Okay. We want to come in. We want to hang out with you. We want to teach you. We want to go on tangent. Get it? Listen, we'll be so happy to give you assignment and not test you ever if everyone's honest and do their stuff. Right? If that's possible.
Depends on if there's specific deadlines. Because if we're talking flexible deadlines, I can do that.
Well, in life, there's always deadlines. Okay, here we go. Example dos. Can you help me, Aaron, with instruction?
Identify each x value which any absolute extreme value is. Explain how your answer is consistent with the extreme value.
Perfect. Okay, so it's asking you to give me x location where if we have any absolute min and absolute max. And how does that relate to extreme value theorem? A max and A min. Let's talk about it. Is it okay to not have any? Yeah. Okay. Natalie, do we have any absolute max? No. Because this is on the top. What's happening? It's a hole. I see a hole in it. I see a hole in it. H-O-L-E. Oh, that's a softball chant. My daughter's. Okay. Absolute min. Tina, any? 2 at x equals, right? At x equals to 2. Okay. Absolute min is 0. Would you agree with that? If I say is 0? Okay. Anybody know what I'm talking about? Absolute min is 0. Okay, in parentheses. Absolute min is 0. What am I talking about? The y value. And notice how at, okay, or you can write x equals, refer to the x, okay? All right, so you do have an absolute min. Then it says, explain how your answer is consistent with the extreme value theorem. The extreme, is this consistent or not consistent? What does the extreme value theorem say? Brian?
If it's continuous on a closed interval, then it's going to be guaranteed to have both the maximum and the minimum. So if it doesn't meet those requirements, then it may not have either a maximum.
Right. What is it violating?
Continuous.
Yeah, the continuation part, right? Continuity is a problem. So we are going to abbreviate extreme value theorem does not, I should say, apply because does not apply because it is not continuous. Okay, because remember the extreme value theorem says both, okay, closed and continuous. This one is closed on the endpoints, but it's not continuous. Okay, why don't you guys try B out? A max, A min, and what's happening to EVT? Extreme value theorem. Is it consistent? Is it not consistent? Oh, yes. Yeah, maybe. These pictures are stolen from Google. I'm not selling them.
Expelled for plagiarism. I just can't believe you get expelled for plagiarism.
Yes, that's cheating. You get arrested in real life if you cheat on tax.
Really? Oh, yeah.
You could be on house.
Brandon S. A max. It's X equals C. Is Brandon right? Yes. Amen. Jason. Yes, no, maybe? Great. Extreme value theorem. Is it consistent? No. Okay. Does not apply because? It's not closed, you're right. Or what? Or continuous. Apply because it is not on a closed interval. Or continuous. Okay. It violates all of it. So that's why there's no guarantee. You can still have them at times, but just not a guarantee. Okay. Okay, so this is where we talk about the local and relative, as Marley was kind of bringing it up earlier. Local is what your book uses. Relative is probably what your Algebra 2 book used, right? Okay, they're exactly the same. Ready? Let C be an interior point of the domain of the function f. Then f of C is a ... Right. A local maximum value at x equals to C, if and only if. And you're going to see that the definition is so similar. F of x is less than or equal to f of C for all x in some open interval containing C. Okay. So look at the definition. Isn't any different? Okay. And then we'll draw a picture and maybe put both the absolute and the relative or the local together. Okay, so, and then 2, local minimum value, local min value at x equals C if only if f of x is greater than or equal to f of c for all x in some open interval containing C. And let me just draw a picture and make up sort of a graph. I'm just making this up. Okay. Let's call this A, let's call this B, let's call this C, let's call this D, and if I can do alphabet, that should be F. Oh, see, I can't do D, E, see? Oh, see? Woo! A, B, C, D, E. All right, thank you for helping me. This is F of X. Okay. Yes?
It's representative of a value.
We're gonna, yeah, it's okay. We're gonna use E. Do not think of it 2.71. E is just a value on the X axis. Okay. So let's look at this one. We're gonna connect both absolute and local together. Question number 1. You have absolute max.
Yes.
How many? 1. You can only have 1 of each unless the heights are exactly the same, okay? Since the height isn't, absolute max is at B. Can we agree? Do we have an absolute min? Where? At E, you're right. Then what do you call C and D? They're locals, okay? C is what? Local min. D is what? Right. But here's the thing. B is definitely an absolute, but it's also a local. Okay, again. Thank you. Or you can turn it around and say D is an absolute max, right? So again, absolute max, it's also a local. But local cannot be an absolute.
So all absolutes are also local?
Yes, sir. Okay. So oftentimes, if it's just asking for max and min, you're looking for all of them. It is. A square is a rectangle, and a rectangle is not a square. Same thing. Okay. Absolutes are min. I'm sorry. Absolutes are also local, but locals are definitely not absolute. Okay. So. All right. Let's theorem. Local extreme values theorem. Am I going too fast? No? Okay. Too slow? No? Right, just right? Okay. If a function, because I know not all of you have printed notes, so if a function f has a local max value or a local min value. And class value means we're talking about the y output, okay? At an interior point, let's call it C, of its domain. And if f prime exists at C, then f prime of C, it's 0. Okay, there's all the fancy wording. Really, really fancy. You tell me in plain English, what does it want you to know?
At the maximum,
At the maximum and minimum, the slope is definitely 0. You agree with that? Aren't those also the turning points mounted too? Did you guys agree with that as well? So at turning points, the slope is, oh, and those are your physics. What's happening? It's changing direction. You don't have to be in physics. That was also the question. I don't know what form you had. But that's when it changes directions, right? Or slightly hanging out a little bit. Okay. So, well, let's talk about tangent then. What's happening to the tangent at those locations? It's horizontal. They're all connected. Okay. So they're all connected. Okay. Critical point. Critical point. Super important for us to analyze the function. Okay. Critical point is a point. So a point in the interior of the domain of a function. Let's call it f at which f prime is 0. F prime is 0. Or f prime does not exist. Okay, so that can be a corner, a cusp, a discontinuity, a vertical tangent, any one of those. Okay, so okay, are we ready to use those things? Can you help me, Miss Isabel Tran, read the instruction to example 3? Thank you. So what this means in plain English, guys, is use analytic method. That means algebraic or calculus method to find any min or max. Okay, it doesn't have to be pertaining to absolute or local. Just find min or max. Okay. So because this is our first example ever, I'm going to spell out everything I do. Okay. So step 1, we should find the critical points. Find critical points, okay, if there are any. So, how do we find critical points? Ben? Okay, take the derivative and set equal to what? 0, or make sure it's wherever is undefined, right? Sometimes it's easy to find undefined, sometimes it isn't. Okay, so we're going to do g prime of x. Well, g of x is e to the x. So what's the derivative of e to the x? E to the x. I love it. Okay. And set it equal to what? 0. Perfect. Let's solve for what? Solve for x. Solve for x. Because we're interested in finding where it is located. Now what? Okay, you can totally natural log to both sides. Now what? Uh-oh. Is this possible, y'all? No. So guess what? Does not exist. Or can I just write D? Okay. So, this function, there will not be any horizontal tangent. Can we all agree? And how are you supposed to tell me to find the max and min? Uh-huh. Oh, yeah, it's true. Isn't e to x is like this really like a lazy curve, right? There's not a, what? A turning point at anywhere. Would you agree? But let's talk about the n values. Is it closed or open? Closed, right? Isn't there a value or a theorem? Gosh, I wish there's a theorem that says. Oh, you mean like there's not a theorem that says if there's a closed interval? Okay. If f is continuous on a closed interval. Oh, bubble. Aaron, can you help me?
I know you can turn off the screensaver.
Oh, you have to help me tomorrow. Okay, thanks, Aaron. Okay, if it's a closed interval, aren't we guaranteed a min and max?
Yeah.
Yes. All right, let's find it. Okay. So second, since critical point is useless, plug in endpoints. Plug in endpoints. And sometimes critical points as well, but in this case, it is not any. Okay. And C. Okay. All right, here we go. And we don't plug into the derivative. What do we plug into? The function, because I'm not interested in the slope. Okay. So your endpoints are at -1 and 1. So g of -1 and g of 1. So g of -1 is e to the -1, which is 1 over e. And g of 1 is going to be e. All right, what do you do with those? Which one is what? No, you have to tell me which one's which. You can't just box it up.
It's the bigger one is the max.
Ah, max is e at where? Thank you. Min is what? 1 over e at where? That's right. Okay. Can't just box up, y'all. You got to tell me which one's which. Marley. Huh? Oh, okay. Okay, yes.
Do you want to include both? Like max is.
Yes.
E
Give me
at
both.
3, or you
Give
want
me
to
both.
both?
Just yep. Give me both. Because it's asking for this actually extreme values. Okay.
Can you just
And
put
where they
both
occur.
then?
No.
Oh, there's one.
Okay, question. Can you just give me order pair? No. Tell me which one is which, okay? Because this one says, give me the extreme values. That's the y value. And then where they occur, meaning where the x location is supposed to be, okay? All right, next, step 1. Find critical points. What do? Derivative. How do you find the derivative of that? No, I'm not saying right or wrong. I'll give everyone a moment to kind of think about it and then answer. Brian knows, Marley knows. It's okay. You can be wrong all you want. It's just notes. What's the derivative of e to the x? E to the x, but. Right. Would you agree? But I need to times u prime. Oops, I just did that. But would you agree that's my u right there? Yes. Okay. So this leads me to e to the -x squared times -2x. We obviously have to make it really, really pretty. Okay. Okay. So now I have the derivative. What did you do with the derivative? Set it equal to 0 is right. Okay. Remember, e to the x, y'all, is a continuous curve. So there shouldn't be any cusp or corner or discontinuity or anything like that, okay? What do you do here? How do you solve x? Isn't this a factor?
Oh my god.
So wouldn't I just take each factor and set it equal to 0? Would that be okay? So over here, I would have x equal to 0. What's over here and to the right? To the right, to the right. Well, right. Right. Would you agree this, again, does not exist? Yes. Exit out. Okay. Does not exist. Can someone tell me why again? Yeah, natural log of 0 does not exist. Log, the domain is greater than 0. Okay. So you have one critical point. Now let's look at the endpoints. Because you're supposed to plug in critical points and endpoints. Okay? But do you have any? No endpoint. Critical endpoints into f of x. Okay? But if you only have 1 point, because there aren't any critical points, there aren't any endpoints, how do you know if that's an x at that location is minimum or maximum?
That is the question.
Okay, so in the case where you're confused, Natalie,
You make a little chart, plug in values.
you're right, make a chart, and in my case, I like number lines, okay? I got 0 in here. Here's your x location. I'm gonna plug in, remember, would you agree that each of the something is a continuous function?
Yes.
Right. So what I'm really doing on this third step is make a number line, okay? At 0, what is your height at 0? Do you know? 1, right? Because that's all I can do in step 2. Would you agree? Well, let me plug it in to see if it's really 1. Would you agree? It's e. 0 squared is 0. Times -1 is still 0. So at 0, your y value is 1. Yes, no, maybe? Yes. Now, the reason I pick large values as -100 and +100 is I want to see the end behavior, right? And it's easy to plug in big numbers. And again, I'm going to do e. By the way, you have a negative exponent. Isn't that the same thing as 1 over e squared? I'm sorry, not e squared. E to the x, e to the positive x squared, like that. Okay. So it's really 1 over e to the 100 squared. Yes, no, maybe? Is that a big value, small value? Less than 1? Yes? I don't know what it is. I don't have a calculator. I just know it's less than 1. It's positive, less than 1. I don't care. Is the same thing at the bottom? Yes, because it's square, right, y'all? Okay? Because it's square, it will always be positive, except that it's positive, but it's still less than? Less than what? 1. Yes, no, maybe so? I'm going to pause right there so we can think about it for a second. Is that a true statement?
Yes.
So what can we conclude? At 0, what's happening? It's max, okay? Max is 1 at where? At 0, or you can write x equals 0. Okay, you can just write at 0 is fine. So I'm going to pause right there so you can ask questions. Okay, so on this example, we did 2 extreme things, okay? The first part, you had endpoints, but no critical point. The second part, we had 1 critical point, but no endpoints. Ash?
I have a question. So we plugged in the -100.
I just found really large values, okay, just to see the end behavior. Does that mean, what am I talking about the end behavior? What's an end behavior? Where the function is going, okay? And this function is going, what's happening is to the, getting closer and closer to what, by the way? 0, isn't it?
If it's e to the x squared, the reason why it's like 1 over e is a negative.
Correct.
So why is it still a fraction when you plug in 100?
Well, I just made it a positive exponent, right? E to the negative x squared, I just made it a positive exponent.
Sorry.
No, I'm okay. Is that okay?
Yeah.
Yeah, so what this is happening is, guys, the end behavior is that the y value is approaching 0. That means there's an asymptote on y equals to 0. There's a horizontal asymptote, y equals to 0, okay? Any questions so far before we go on to the next one? Okay, ready? Here we go. Sarah, can you help me read the instruction, please? Isn't it the same set of directions? Yeah, okay. So, I'm going to do the same thing, except I'm not going to spell it out anymore. Step 1, what would you do? Yeah, and if you want to, you can still just write critical points. All right, let's do y prime. Y prime is 3x squared minus 2. Set it equals to 0. Yes, no, maybe?
No, it's not 2x.
I'm sorry, I said 2 and I wrote 2x. Thanks, Brian. Good eye. Okay, now what? Solve for it? Okay, solve for x. So 3x squared equals 2. Yes or no? Divide both sides by 3. So 2 over 3. Now what? How many answers are you going to have? Good job.